Hello everyone, we are group Hakuna Matata. Our group leader is Lin Zhiyu, and team members are Hu Qingyi and Huang Yushan. First, let's talk about our specification of the work and references. Since our main goal is to minimize the area, we adapted group Angogo goals idea of using carry bit for extract and exclude, and group LC's idea of reusing adders for comparison. The improvement is that we modified our previous comparison circuit, which includes a combinational circuit between D flip-flops into adders. It not only stabilized our system, but also reduced the area. However, its drawback is a longer time will be held. Next, let's look at the algorithm. We have input signal of clock, function select, reset, and IoT inputs, and output signals of valid, busy, and IoT outputs. To generate functions, we first need two kinds of counters to help us count what the current cycle is and what the current round is. This will help us decide what our next action is. Following are the algorithm of output busy and valid. For busy, add function 1, 2, 3, 6, and 7. Once a round is going to be ended, it will generate a high signal with a clock width. And in function 4 and 5, once a round is going to be ended, it will generate a high signal with 2 clock widths because we need 2 cycles for subtraction. In other cases, busy will stay as low, indicated the IOTDF circuits can receive a new data entry. And for valid, if the current function is extracted or excluded. When we finish 2 rounds of computation, we will generate a high signal at the next clock. Else, we will generate a high signal before each round is reset. As for our computation of each mode, if the function select is max, then we will use adder to do comparison and store the result at the ACC register, which will be reused until the round is completed. After computation completed, we will send the data to IoT output. Min is similar to max, but we choose the one with smaller value to be stored. In function of average, we will add every value together and right shift 3 times before data output. For extract, we will store every number lower than high bound and every number higher than low bound into ACC reg, and then send them to IoT outputs. Offset to extract, exclude will store the value higher than high bound and lower than low bound into ACC register. Both extract and exclude requires 2 times of computation. We compute with higher bound in one clock and then compute with lower bound in the next clock. For pick max, we will select the maximum data and store it in another register for next round of comparison. After the second round completed, we send the results to IoT output. Similar to pick max, pick min selects the minimum data and store it in the register in the first round, then compare again. Output the results in the second round. Next, let's talk about our system architecture. Following are 2 types of counters that are used in our system, which counts in bytes and counts in 128 bits data respectively. Here is the full screen of our circuit. When data is stored, it will pass a 128-bit register first and then sent to another register for later on comparison when the data is completely sent. We use a 131-bit register here for component reuse. This is the components we use for max function. Data first stored in a 128-bit register, then compared with the previous state ACC register. After passing the 130 bits adder, the result will be stored in the ACC register, waiting for the next stage comparison and output. Min and average are similar to max function, but we select the smaller data in min and use addition in average. For function extract, We will compare with high bound first, and then compare with low bound in the next clock. After that, we output the data. For function exclude, the data path is equivalent to function extract. For peak max, we will store the first round results into peak max main register, and then compare again in the next round. After computation, we output the results. Function peak min is similar to function peak max. Our known and to be learned issue is that our coding style in this design is software-oriented. Thus, the actual hardware circuit architecture is not very clear. At the same time, the area may become larger because of it. Therefore, we consider changing the coding style to be more hardware-oriented. And this is our RTL path simulation from function 1 to function 7. For function 1, in this waveform, when each 128 bits data input is complete, it will be compared with the data in ACC register. The larger one will be stored back to ACC register. Signal valid will convert to high after each round to output IoT out. For function 2, we need to initialize the ACC register with the biggest value before the burst data is completely loaded into the in register. Then perform the same operation as function 1 on all the data and select the smallest data in each round. For function 3, the accumulated value after each addition will be stored back to the ACC register. At last, after the last data of each round is loaded, the addition is performed again and the third to 130 bits in the ACC register will be the output. For function 4, when each 128 bits data is completely loaded, the signal BZ converts to high. In the first clock of BZ equal to 1, this data will be compared with the high bound, and in the next clock, this data will be compared with the low bound. If this data should be output, then signal valid will be sent to high and output 128 bits data in this cycle. Function 5 is almost the same as function 4. In function 6, its operation mode is similar to function 1, except that not every round will exceed output data. Data will be output only when the signal valid is high. And function 7 is almost the same as function 6. Here is a gate level simulation of our design. The total cell area is about 32,000 times micrometer square. The data required time of our design is 29.33 nanoseconds. Besides, the slack values in max and min type are all positive. Following is our to-do list and member job assignment. This is our ideal project work schedule that was scheduled in our previous presentation. And here is a work schedule in reality. It was lucky that our exams were held on different days, so we can have progress at this very first days. However, our progress stalks for several days due to the final exam week. The postponement of progress makes our progress frozen, and as a result, we have an intensive schedule at last. We hope we won't face the same problem again in our final paper submission. Next is our possible issues and expected solutions. The possible issues and expected solutions is that after logic synthesis, if the clock period is too short, then it will cause timing violation. And one of the expected solutions is to choose another kind of 131 bits adder, which has lower propagation time delay, because in our design, adder should be used in every function. The other solution is to extend the clock period in the test bench. That's all for our progress presentation. Thanks for your attention.